What's up? What's up? What's up? It's your boy, the network. And today's topic is subsection 3.2a Unicast, which is a subsection under the section 3.2 identify IPv6 addressing and subnetting. This is a section in the exam CCNP route exam code 300-101 version 2.0. Let's take a look at the exam blueprint to see where we came from and where we are headed. All right, this exam blueprint, implementing Cisco IP routing, exam code 300-101. We just wrapped up DHCP protocol operations. That's my favorite subject, DHCP. And we are now moving on to identify IPv6 addressing and subnetting. Don't be alarmed. IPv6 is not that bad. Matter of fact, it's the future. We are doing today 3.2a alpha Unicast. After that, we're going to be moving on to 3.2b EUI 64, which is a way of auto-configuring an IPv6 address onto your interface using the MAC address. And I will show you that in the next video. Today, we are doing Unicast. So, remember we covered Unicast a couple videos back right here, section 3.1a. That, however, was for IPv4 addressing. Today, we are covering Unicast concerning IPv6. There really ain't no difference. It's the same thing. It's traffic going from one device to another device, one-to-one communication. Only difference is the IP addressing. Instead of using IPv4 addresses, they use IPv6 addresses to communicate with one another. Let's head over to the slides and take a look at the official definition of Unicast traffic. We mentioned it in the other video, but for now, this is IPv6. So, same thing with IPv4. Most network traffic is unicast in nature, meaning that traffic travels from a single source device to a single destination device. They are addresses assigned to a single interface on a device. They are used for one-to-one communication, just like I mentioned before, whereas broadcast is one-to-many, and multicast is one-to-some, basically. And there's also Anycast, but I don't think we're really going to cover it. There's no really blueprint. I may do a bonus video on Anycast traffic, which is for IPv6. However, there's no broadcast in IPv6. That's something else that you should take note about. Now, if you notice here, we've got traffic from router 1 going to the server up here. He just sends the traffic through the cloud or the internet, whatever you want to call that, ISP, to the router, to the local area switch, to the server. That's all it is, and back if it's a ping. So the only difference is the addressing scheme. That's an IPv6 address right there. It's just been in a compressed format because the IPv6 address, I'll give you a couple examples in the next couple slides. But it actually is divided, and you know how IPv4 addresses are separated into 4 octets, right? Well, IPv6 is divided into 8 sections of numbers, and they're all 4 numbers. Hexadecimal format, though. All right, so here's the differences between IPv4 and IPv6. Remember, you got to know where you came from to know where you are headed. IPv4 was deployed in 1981. IPv6 was deployed in 1999. Now, keep in mind, these were in, they were in development before, like for IPv4 been in development since like the early 70s, and then IPv6, I believe they came out with that in like 1993 or something like that. And they ain't deployed until like 1999. Same thing with IPv4, they ain't deployed until 1981. The address size and difference is 32-bit number. It's a 32-bit number. IPv4 is 128 in IPv6. You can see the addressing format right here. It's in dotted decimal notation, whereas IPv6 is hexadecimal. If you don't know what hexadecimal is, let me give you an example of that. This is a hexadecimal chart, conversion chart. So it's real easy to really to use. From 0 to 9, you just know they're the same thing in hex. Once you get past 9, it's 10 through 15 that you just got to start converting. 10 is equivalent to A. 11 is B, so on and so forth, all the way to 15. So 10 through 15 is the same thing as A through F. That's all you really need to remember. But if you need to do the binary conversion, that's what they are right here. You should know this by now, the binary part. It's the decimal to hex conversion is what you really need to remember as far as IPv6 is concerned. So That's the prefix notation. This is the number of addresses. Now, if you can see the sheer difference in amount of numbers between IPv4 and IPv6. Now, IPv4, as you can see, this number, it's 2 to the 32nd power is that number. That's like 4.2 billion, basically. So when they invented IPv4, there was like 4.2 billion addresses. Psh, we don't need to create any more than that. That should last us for many, many years. Well, you know what? It ain't last them no more than about a decade. It took them maybe about 5-6 years until they found out, like, we're going to run out of this pretty quick, maybe about a decade. But so they started working on IPv5, and they realized that wasn't really working out, so they created IPv6. That's why I skipped from IPv4 to IPv6. IPv6 has 2 to the 128th power. That's basically this number right here. That 340 something. It's like undecillion. It's in the next slide. I ain't even heard of that number before. So this, again, is the hexadecimal conversion chart. You can pause it right here if you want to look at it, freeze frame it, whatever. Screenshot it, whatever. So this is just to give you an idea of the amount of IPv4 to IPv6 addresses. As you can see right here in this light blue line or arrow, IPv4, we had 4.3 billion addresses available. Now, with the advent of everybody damn near having a cell phone, and then pretty much everybody in the world, you know, different countries started implementing and getting on the internet, we started running out of IP addresses really quickly, especially like in the mid 90s. And then, you know, we started running out of really quickly. As you can see, it's 10 to the 9th power, right? That's how many addresses we had. So they started working on it, IPv4 or IPv5. That wasn't working out, so they came out with IPv6. Now, that number right there, 1 undecillion, right? I don't even know I'm pronouncing that right. That's 10 to the 36th power, right? This long-ass number right here is 1 undecillion. Well, IPv6 got 340 undecillion. That's how many numbers, how many IPv6 addresses there are available. They pretty much said for every human being on this earth, each human being can have like 1 billion addresses, right? So as of today, this video is in 2018. We got like 7 billion people on this earth, right? So each one of us can have about 1 billion IP addresses. That gives you the idea, amount of how many IPv6 addresses there are available. So that should last us a long time. But you know, with so many things going on the internet, you know, we got Internet of Things, you got microwaves, you got cars, you got stoves, everything, cars, everything is getting on the internet, and it requires an IP address to do so. So that's how come we running out so quickly. But that should last us a long time. There's only a couple of countries that's fully using IPv6. I believe it's either Denmark or Iceland. I don't remember. Somewhere in Eastern Europe, they're the only country in this world that's really fully implemented IPv6. But I bet you if you look at your cell phone right now, you should have an IPv6 address available already on it. Shout out to Professor Graziani out of Cabrillo College once again. I just realized he's a Cisco Press author too. So here's the difference between the IPv4 header and the IPv6 header. That's for how many available addresses there are available for IPv6. We got to do that. So as you can see, the IPv6 header is a bit simpler than the IPv4 header. They took out a couple fields. Header length was removed because IPv6 is a fixed size. It's like 40 bytes, whereas IPv4 header, I believe, was 32 bytes. Yeah, I believe it's 32 bytes, but IPv6 header, yeah, it's always 40 bytes, so that's a fixed amount. That's why they removed that. Fragmenting, remember what we talked about in the fragmenting video. I don't remember which video that was. Let's check. In this video right here, 1.3b, I mentioned that fragmentation is not even possible in IPv6. You can't even do that. So that's why they removed that. They remove the fragment offset field from the IPv6 header. They also removed a header checksum, options, and padding. So as you can see, the IPv6 header is a bit simpler. Go ahead and pause this if you want to take a look at it, screenshot it, whatever. All right, we're back. We're moving on to the next slide. So, as far as IPv6 addresses are concerned, it's a long ass number, right? I'll give you an example right here. So this right here is an example of an IPv6 address. This long number right here. Remember I said they're divided in hextets, whereas IPv4 is divided into octets. Well, there's 8 hextets, right? Hextet is not the official name, but that's what we call it. These little separations right here, right? Now back to what we was mentioning before. IPv6 addresses, we can compress them because they are so long. You know, it gives us more of a chance for human error. You know how you ping an IPv4 address, not 9 times out of 10, but sometimes you make mistakes, right? Imagine trying to type that long ass number for IPv6. Well, they have compression, so you can minimize that'll minimize human error. Most likely you'll still make a mistake, but that kind of minimizes it, and it makes it a little easier to type. So there's 2 rules you can do to shorten it or compress the number. You can remove the leading zeros. Right here, as you can see, omit leading zeros. This can be done in any hextet and turns 0001 to just a 1. Now remember, you can only do this with leading zeros. Now, you can only remove leading zeros. You can't remove a trailing zero. So if you got a number like 1,000 in a hextet, you can't remove the last 3 zeros. So this I messed up right here. The second part is to remove. You can represent one hextet with a colon and consecutive hextets with a 00 if it's contiguous zeros. So if you got 4 zeros, you can compress it to just a single 0 because you remove the leading zeros, right? Or if you got a whole bunch of zeros, you can compress it with just a double colon. I'll give you a couple of examples in the next couple slides. So here's the first rule. Once again, you can remove leading zeros in any 16-bit segment. Again, these are hextets. They're 16 bits each, right? So for example, this is the first IP address. The next one would be the compressed address. Same thing with these guys. Uncompressed, compressed. Uncompressed, compressed. On the first one, we removed the leading 0, right? We removed the leading 0 and turned it to VB8. Same thing over here. We removed these 3 leading zeros, turned it into 1. This is 1,000. We can't remove these because these are trailing zeros. So you can't remove that. That's just 1,000. This right here, we removed the trailing zeros. The leading zeros and turned it to just a 0. Same thing here. Now, the thing with these 2 zeros right here, these are 2 contiguous quad zeros. We can turn this to a double colon. It ain't shown in this example. This is just to show you rule number 1. But we can turn this into a double colon. This right here. This right here, we remove the leading 0, turned it to EF0. We can't remove that 0 because it's a trailing 0. And this right here just remains the same because this only has trailing zeros. You can't remove the B and the C. This uncompressed format right here is another example. We remove the 0, it's a leading 0. Remove this, that's a leading 0. Remove these 3, leading 0. Remove those 2, leading 0. This stayed the same because these are trailing zeros. Y'all see that? This right here, trailing zeros. We kept that the same. This right here, leading zeros, we removed it. So this is the uncompressed format of this version, of this number, IPv6 number. Now this IPv6 address, same thing. We removed the first 0, leading 0. Remove these leading zeros. Leading zeros, leading zeros, leading zeros, leading zeros. Now, what you think we could do with all these zeros right here? Pause it and think about it. All right, we back. You can remove all these zeros. You can put them just single zeros like that because they're leading zeros. Or you can put double colons like we mentioned. That's the second rule. I didn't go too much into it. But the first rule is you remove leading zeros, right? This is a leading 0. Removed it, turned it to 500. This is the uncompressed format of the above number right here. IPv6 address. Moving right along. Again, leading zeros, you can only do the leading zeros. You can't remove trailing zeros or else it leads to ambiguity, meaning the router is not going to know which 0 you removed if you removed the trailing zeros. That's why you can only remove the leading zeros. Here's an example. This AB right here, since we know the rule, we remove leading zeros, right? But how does the computer know it or the router know it if it's a trailing 0? Notice how if it's a trailing, we got a trailing 0 and a leading 0 right here. How does it know if it was leading 0 or ending 0s? That's why you can only remove leading 0s. Notice here, leading 0s. All right, second rule to reduce this even further, quad 0s like that, you can turn them into a double colon, right? That's what it says here. Second rule, any single contiguous string of one or more 16-bit segments consisting of all zeros or quad zeros can be represented by a double colon. So this right here turns out, you can pause it and think about this to see what the answer is. All right, we back. So the answer is, we got 2000, right? We removed the leading 0 right here. Can we remove these zeros? No, because they're ending 0. So this stays at 1000. These zeros right here, they're quad zeros. So this turns into a double colon. You can put them all single zeros, but to compress it even further, you just put double colons. Right? So we remove those guys. And then these are leading zeros that we can remove as well and turn that into 1. So the compressed version of this address will turn into this number right here. 2001 DB8 1000 double colon 1. That make any sense? Now, I'm going to leave a link in the description below in case I forget to tell y'all. Subnetting, I believe it's practice.net, subnettingpractice.com. I can't remember. Let me double check. Yeah, subnettingpractice.com. You go to the IPv6 section and you can practice these numbers and how to compress it. It's a great way to, I was doing it so much. I took a nap today and started dreaming about IPv6 addresses. Swear to God. Shout out to Professor Graziani out of Cabrillo College for these slides. Rule number 2, again, double colon. Now, if you got 2 sets of double colon or quad zeros, you can only use this rule one time. As you can see right here, it says, although the rule states both of these are correct, right? That you can use double zeros or quad zeros like that, but you can only compress with a double colon one time. So on this, you can put a double colon either on this side or double colon either on that side, but you can't put it on both sides. You got to pick one. As you can see right here, this number turns into DB8 double colon single zero 5678, or you could turn it to single zero 1 2 3 4 double colon 5678. That makes sense. That's the RFC right there. Again, maximum reduction of this address is also known as the compressed format. So when it's uncompressed, it got all the zeros. It look like a long ass number. When it's compressed, you'll see single zeros and you'll see double colons in it. It'll look shorter than you know. Just remember, when it's compressed like that, there should be 8 hextets, right? But if you only have, like, say, it looks like it only has like 3 hextets, then you know you're missing 5. So that's something you need to remember. It's supposed to be 8 hextets, but if there's missing a couple, then you should know, just simple subtraction. That will give you the uncompressed format, rather. So again, this is rule number 2, double colon. You can only use it one time. That's what that number turns into. Here's the uncompressed number. So there's multiple types of unicast addresses. We're going to go each one of them on each one of these slides, these next couple. If you want to look right here, these are the 5 types of unicast addresses. There's one more, I believe it's like embedded. We're not really going to cover that, but that's basically, it's kind of like, it's almost like tunneling, but it's like a combination of IPv4 and IPv6 address. IPv6 and IPv4 address, but we're not going to go over that. So there's global unicast, which is sent through the public internet. Link local, which is sent only in a local subnet. Loopback, which is quad Z, which is all. Notice how this number is double colon, right? So that means it's all zeros and a 1. That's the same thing as 127.0.0.1 in IPv4, which is known as the loopback address. Unspecified has no IPv6 address. Unique local, which starts with FD, but it also starts with, I believe, FE80. I'll show y'all in the next slide. Again, global unicast address is sent through the public internet. So this is the same thing as using the public IP address, like, I don't know, 120 or a number that's not a private IP address. This is what you could use on the internet, and it's routable on the internet. It'll start with a 2000 like this. It's global. That's the reason why I put these little images right here of a globe, 2000. That's how you know that's a global address when you look at the 2000/3. That's the prefix right there, 2000. For a linked local address, it'll start with an FE80, and their prefix is FE80. This is the same thing as a 169 or a PIPA address in IPv4. So that means what? You can't use it. It's not routable on the internet. This is only something you can use locally within your organization, within your subnet only. In that subnet, even if you got 5 subnets within your organization, this address can only be used in one subnet. It's also used for neighbor discovery, which we will cover in section 3.2. That's what ND means, neighbor discovery. Again, the loopback address is all zeros and a 1 at the end of it. So if you look at this number, the uncompressed version of it is all quad zeros, 8 sets of them, right? But the last number is a 1, similar to 127.0.0.1 in IPv4. It's a loopback address. If you need to know your computer's up, you ping that, : 1. That tells you, whether, the IPv stack, TCP IP stack is working on your computer or not. Unspecified is used when a host has no IPv6 address. It's rare that you're going to run into this. Again, look at your cell phone right now and look at the IP addresses on it. I bet you got an IPv4 and an IPv6 address. God forbid you got an iPhone, that's going to have an IPv6 address too, I bet you. So it's going to look like this, all zeros, /128. So this is kind of like /32. It's almost like a loopback, but this is all zeros, /128. Then there's the unique local address, which is used only in one organization, similar to IPv4 private addresses. So it's kind of like, how with IPv4, you got the 10 network, the 172 network, 172.16 through 172.31, 255, 255. That's a private IP address range. And there's also 192.168 network. That's also the private IP address range. Well, this is the equivalent to that in IPv6. The prefix is FD00/8. I'll give you a couple examples as well. Matter of fact, there's one right there, FC00. Now, this is a form that I found on the Cisco Learning Network. If you don't have an account for that, you need to sign up. If you're studying for any like CCNA, CCNT, you need to create an account with a Cisco Learning Network. It's learningnetwork.cisco.com. As you can see right here, this answered one of my questions right here. Not my question, but when I was looking for it, it came up in here. These are the different types of unique local, linked local, and global unicast addresses. I didn't show them in my slides here, but as you can see, linked local also starts with FE8, FE9, and FEA. He wrote it twice here, but this pretty much answered my question. Again, when you get a chance, sign up for the Cisco Learning Network. You will get a lot from that forum. I'm not sponsored by them or anything like that, but it's a great resource whenever you're studying for any kind of Cisco certification, even networking in general. And if you like this video, that's the end of the slides. If you like this video, please comment, like, subscribe to the network.